Alright, so we're going to get started in a new chapter, chapter 3. The title of this chapter is Primes and Their Distributions. Okay, we are all familiar or know what a prime number is, even though we will define what a prime number is. Then we're going to study in this chapter a lot of properties of primes, and in particular how they appear among the natural numbers. That's what we mean by the distribution. Means, are they clustered? Is there some clusters of primes very close to each other, or are the prime numbers, there are a lot of gaps between them. If there is a prime and there's a lot of, numbers that next to this prime, could be very long, sequence of composite numbers, and then there's another prime show up, or we're going to look at how, two consecutive primes, in some sense, means a prime, and then we have another prime that exceeds this prime by 2, okay? These are called the twin prime. So we're going to study a lot of these properties. So we're going to get started today on section 3.1, and this section we're going to have one main objective. This is the title of this section is the Fundamental Theorem of Arithmetic. All right, maybe the name looks strange to you, but it's a very familiar theorem that you use your entire education, even from starting from second grade, third grade, and so on, without knowing that this is what is called the, as I said, the Fundamental Theorem of Arithmetic. So this is our main objective, is to state and prove this actual theorem. And to achieve this goal, to achieve this main objective, we need to get started by giving an important classification of natural numbers. Probably you are familiar of some of the classification, or sometimes we call it partitioning of the natural numbers. One of this classification is to classify numbers as being even or odd, okay? And so a number either is even or odd, and they are defined, of course, in a very simple way. Other classification of numbers may be talking about numbers being square or not a square, all right? A number is a triangular number or not a triangular number, and then many other classification actually. All right, the classification we have in mind here is for a number to be a prime or not a prime, composite, or what else. Okay, so we're going to see this. Then we're going to prove some preliminary results concerning primes. Okay, and these are needed to again get to the fundamental theorem. Then we're going to give an example, or examples, actually, a couple of examples of number systems that does not satisfy the important property of this fundamental theorem of arithmetic. Is called unique factorization. All right, property means there are some systems, they share a lot of properties with the natural numbers, but it turns out in these systems the unique factorization does not hold anymore. All right? And then finally we end with looking at some applications of the fundamental theorem of arithmetic. All right, so let's get started by preparing the way to define what we mean by a prime number. So let's assume that we have n is a natural number. Sorry, actually it's an integer, it doesn't have to be a natural number. So let n be an integer, positive, negative, 0. Then if n equal to 1, then n has only one positive divisor, which is itself, of course. And here we are interested in positive divisors. Of course, it does also have -1 as a divisor. All right? However, if n does not equal to 1, then n has at least 2 positive divisors namely 1 and the absolute value of it. All right, in case n is a negative number. Now, this classification or this property for integers, okay, to have, only one positive divisor or at least 2 positive divisors. So we're going to look at those integers which have exactly 2 positive divisors. We call such numbers, okay, actually prime numbers. And we're going to here only consider those that are natural numbers, means they are bigger than 1. Okay, so here's the definition. So a natural number n is a prime number or sometimes simply a prime if n has exactly 2 positive divisors. All right. On the other hand, if n has more than 2 positive divisors, this is equivalent to say that n is not a prime. Because this one says has exactly 2, all right? This one has more than, okay? More than 2, all right? And this more than 2 doesn't have to be actually this distinct, means they don't have to be different, all right? Then we go when n is called a composite number. All right. Now, let's put a few remarks in here. Okay. More spacing. Go ahead. So from this definition, it follows that the natural number 1 is neither a prime or composite. So it is, in this classification of numbers, 1 is a class by itself. Okay? Mark. All right. The first one is according to the above definition, according to definition of primes and composite numbers. Actually, go here. One is either a prime nor composite. So in other words, we have three classes of natural numbers. We have one, we have the prime numbers, and we have the composite numbers. And there is no overlap. There is no number that is common between these three types of numbers. And all of these, when you put them together, we come up with the set of natural. Now, so by definition, a prime number is a natural number. It means it can, we don't take, negative primes. We can take the negative of prime, but we don't call it a prime, okay? So this is just by the definition. The other remark is if he is a prime, the only two divisors or two positive divisors of P are 1 and P. And remember, a prime is that natural number that exactly two, and those are the 1 and the P. All right. So our objective is to show that, to state and prove actually this fundamental theorem of arithmetic. The fundamental theorem of arithmetic simply states that any integer, okay, it's either a prime, or actually, let's say that to a natural number. Okay, let's stick to natural number. Any natural number that does not equal to 1, okay, it is either a prime itself or it is a product of a finite number of primes, and the primes that appear in this product are unique apart from the their order in the product, in where they appear. All right, we could switch them, but they would be the same primes, just in different positions. All right, we're going to state precisely this, okay? But in order, again, to get there, we need some properties to prove about prime numbers. Some of these are very, very simple, and some maybe not very simple, but not very hard to accept from a first look, but they need proofs, okay? So, and this is the main objective of this course, is even some of the very trivial results that we need to present proofs to them. All right, so I want to start with a lemma. It says that if P is a prime, then for every natural number A in N, either P divides A, or the greatest common divisor of A and B is equal to 1. All right? So put simply, all right? So if you have a prime, all right, then this prime divides A, means it is going to be contained in some sense in A. If not, then the greatest common divisor then has nothing to do with A. Okay, B has nothing to do with it. Either it's part of it or nothing to do with it, basically. All right? And this is a very simple. Okay, so let's start proving it. We know that the greatest common divisor of any two integers is either 1 or bigger than 1. It cannot be negative, okay? So either the greatest common divisor of A and B is equal 1, or greatest common divisor is bigger. Of course, if it is already equal to 1, we are done. In other words, if it happens that for some A in N this is equal to 1, then we are done. But since we are talking about for every, so it is possible we have the other scenario. Okay? So on the other hand, if greatest common divisor A, B is called D bigger than 1, then we must show we have the other case, that B divides A. All right? So let's go ahead and take this case. Now we know from the definition of greatest common divisor that D is going to divide both numbers that we are taking there, greatest common divisor. So D equal greatest common divisor, AB implies D divides A, and D divides B. Now, from here, so D is a positive divisor of B. So this implies that D is 1 or D is equal P. But we are assuming that we have P bigger than 1. So in other words, this implies we only have D is equal to P. All right? Now, let's see what we have in here. So this means from here now, okay, together with this implies D, which is equal to P divides A, and we are done. All right? So we have shown that P actually divides A. So that's it, there's nothing to it. Okay, let's look at a more important property. And this is actually theorem 3.1. Okay. And it says that let B be A prime and A, B are integers such that B divides A. Then either B divides A or B divides B, or of course both of them, okay? Now we didn't prove this earlier, but for the sake of completeness for this section, we're going to go ahead and prove it again. All right? Here it is. So if it comes to a number, then it either divides another number or it doesn't. So in our case in here, if B happens to divide A, then we are done. For a pair of integers A and B, and where this condition is satisfied, if it happens that this is the truth, then nothing to prove. Okay? So let's assume that it doesn't. B does not divide A. Well, this is going to force us, okay? So we have to show, we must show B is going to divide B. All right? So we have no other choice except this. Now, let's actually apply the dilemma, by dilemma. Since B does not divide A, then the greatest common divisor of A and B must equal 1. This is what the other, possibility when B does not divide it. Now, from here, this implies by the Euclidean algorithm, this implies there exists x, y, and z such that ax plus by is equal 1. We're going to play with this a little bit, okay? Now, I need to, this fact that which we haven't used so far, that P divides the product. Since P divides AB, this implies that AB equal PR or sum R in C. Now let's substitute for AB, all right, in that last equation. So we're going to substitute for AB and by, of course, PR in equation. I put a star on this. So this becomes actually, let me see it here. In fact, I don't have an AB. So let me actually multiply. Before we do this one, let's me actually multiply. Let me actually go from here, and I will have that in your question. So I'm going to multiply by B. So we get in here ABX plus B squared Y equal. Okay? Now, I want to substitute in this equation by AB. So the equation becomes PRX plus B squared. Don't think I'm going the right way here. Let me see. Yeah, that's why I'm multiplying by B. Okay. I'm sorry. This one's supposed to be the prime. Something is not going right. Okay. Sorry. Okay, so I'm going to multiply this by b, and what I get is abx plus pby is equal to b. All right, I'm going to substitute for AB. Okay, so this is AB, and this one, it has the prime, BY is equal to B. And now I have a common factor. The B, I can take it out, and this is Rx plus BY equal B. And this is exactly what it means for P to divide E, because P is a multiple of P. Okay, so this is, if I call this number a C in here, then actually P is PC. All right, and this is it. Of course, you could, say that if we reverse the argument in the sense of P divides B, then we can show that or the greatest common divisor rather of P and B is equal to 1, then or is not equal to 1, then P that divides A. All right? By symmetry, of course, we don't need to do this. All right, here's a corollary, which we're going to see very useful, where instead of a prime divides a product of 2, it may divide a product of n numbers. Okay, so this is corollary 1. Again, let P be a prime. And A1 up to AN are integers such that P divides A1, A2 up to N, the product of these. Then, included, P divides AI for some I with 1. In fact, it may divide more than 1, but at least it does divide 1. All right? We're going to approve by actually induction on the number of factors, the number of AIs. Okay? So, by math induction on n. So if n equals 1, then P divides A1, and we are done. Okay? And this is the true is the statement which we're going to try to show that P divides, if P divides this, okay, then P divides BI, and this is true for any n, okay, for any n. Yeah, maybe you actually should say it in here, so this is for some, and this is for every n. Well, it's implicitly there, but we will spell it out. Also, if n is equal to 2, and P divides with the product of 2, then by the theorem, 3.1, the statement is true. Then P either divides A1 or P divides A2. Now, let's assume, actually we are using the strong, or the second principle of math induction. So let's assume that me see if I want to actually use it. Actually, no, it's not the second principle, it's the first principle. So let's assume that if E divides A1, A2 up to AN, then P divides AI for some I between 1 and n. May I actually say it a little bit stronger in here. Assume that for some n bigger than or equal to 2. Let's assume that if for some n bigger than or equal to 2, if this implies that, okay? All right, then let's consider actually a product of, and the numbers in here we want to show it is for any number, not necessarily the one which we started with in here, okay? We could use different letters instead of A's, we could use B's or C's, but sometimes we're convenient to change those, okay? Let us consider this. P divides A1, A2, up to AN plus 1. All right? Now, we can think of this actually as P divides B AN plus 1, where B is the product of this. All right. So once again now, by the theorem, theorem 3.1, we have P divides a product. We could think of these as like two numbers, right? And this implies that P divides P, or P divides AN plus 1. Now, if it happens that if P divides AN plus 1, then we are done. Right? Because the mathematical induction, it says that, well, we assume it is true for n products, okay, then it's true for n plus 1 product. However, we need to look at the other case. On the other hand, if it doesn't mean P divides P, then we have P divides A1, A2 up to AN, and by math induction, by inductive hypothesis rather, P must divide AI for some. So in either case, for some I between 1, in math induction, show that this statement is true for all possible, enterprises. All right. All right. Let's move to another corollary, also of significance use. And this deals with if those A's happens to be primes themselves, and P divides a product of primes. what can we say? Okay, so this is corollary to let P Q1 Q2 Qn P prime if P divides Q1 Q2 up to Qn, then it's not just P is going to divide one of these, it's going to actually equal one of them. Then P is equal to of I for some I between 1. All right, here's the proof. We know that from the corollary, we have P divides Qi for some I between 1 and n. Now, this implies that P is going to be a positive divisor of Qi. So this implies that P is a positive divisor of Qi. And of course, P does not equal to 1, right? We also have 1, a positive divisor of a Qi, and since the Qi is a prime itself, is a prime, then the only way this could happen, that then P must equal the Qi because it only, has those two divisors in order for it to be a prime, so it must equal. All right? All right, let's move on to actually, it turns out that theorem 3.1, the converse of it is true. Okay? Means if there is a natural number that satisfies a property, if this natural number divides A and B, product of A and B, then it must divide one of them, then this number is a prime. Okay, so let me write this is as a new theorem. And this is the converse of theorem 3.1. Okay, let me state this. Let me actually use P, okay? Let P be a natural number that satisfy the following property. For every A, B, and N, if B divides AB, then B divides A, or B divides B. So if this is the case, then P is a prime. Is the prime. All right. Later on, we're going to put all of these into one theorem. And we're going to do this one by contradiction. Okay. Now we're going to assume that P satisfies a given property but P is not a prime. Means equivalently means P is composite. All right. So P being not a prime or composite, this implies that there exists a Q in N, natural number, such that the Q does not equal 1 or P, and it does divide. It is a positive divide, okay, of P. All right. Now, let's see what does this mean. This means that if Q divides P, this implies that Q, and it is positive, it's a natural number, okay? So this means that the Q, all right, is going to be smaller than P and bigger than 1, all right? Because P is going to be a multiple of that, all right? Or actually, let me do a little slightly different. This implies, okay, so this implies that P is equal to QK, okay, for some K, and the K is actually between 1, but it's going to be less than, all right? Same thing is true for Q itself, all right? Now, then we have in here another property or another thing. P itself divides P, but I'm going to substitute for this P by QK. All right. Now we're going to use the given property. By the given property, we have either P divides the Q or P divides K. All right? And so from this, well, we have both actually let me actually also in here, we could add one more thing. I'm sorry. We could actually also say it in here that Q actually is less than P and this is bigger than 1. So both of these. But both Q and P and K, sorry, these are less than P, okay, bigger than 1. Now, when we say that from here or here, this would imply that the Q is, this way we could say this one is less than or equal. We could have actually less than or equal in here. All right? But in here, it must be actually strictly less than P. All right? This one is, we could have equality. All right? No, we cannot have equality because it's not equal to P. Sorry. So this means that this tells us that this one is less than P, or this, it says that the other way around. Actually, Q is bigger than P, or K is bigger than P. But this contradicts this statement right here. So these and these give us a contradiction. This gives a contradiction. So we go back and figure out what's wrong is our assumption that actually this P is not a problem. Everything else actually does work. All right, so we can now state that both the theorem 3.1 and this converse in one statement. And here it is. So this is a theorem. And this is theorem 3.1 and its converse. And it reads like this, that B, A, B actually natural numbers. Such that P divides AB implies P divides A or P divides B if and only if B is a prime. So let's think about it one more time. So here it is. If this one implies this, then we have B is a prime, and if B is a prime, we can reverse this. All right? Of course, we have proved this one. We don't need to reprove it. All right. Now let's see if we are ready to actually for another theorem that's going to be important in proving the fundamental theorem. And here it is, another new theorem. If n does not equal to 1, and n is an integer, all right, then n must have a prime factor. Well, very important, okay, because this is the basis which we're gonna actually start working on the fundamental theorem. Now we know that in either itself is a prime, all right, or actually it is composite, since it does not equal to 1. Since n does not equal to 1, then either n absolute value of n, if you wish, because we're taking natural. Let me actually take this to be just natural now. Okay. All right. And then either n is a prime or composite. Once again, if n is a prime, we are done. Okay, because then n actually p is the prime factor of itself. Okay, so if n is a prime, then we are done. Since again n is a prime factor, of n. On the other hand, if the other hand if n is composite, all right, in this case, we're going to define, okay, if n is composite, we define a set S to be D in n such that D is bigger than 1 and D is a divisor of that. All right. I claim that, of course, this is a subset. Okay, S is a subset of natural numbers. This is a subset of natural numbers. Now I hope you will see what we need in here. Okay, so a subset, and I'm going to see that this is not empty. All right, and S is not empty since, all right, so I must have at least one positive divisor, and that positive divisor is actually in itself, all right, since actually n belongs to n divides n. All right, and of course, it is bigger than 1, then n belongs to S. All right, so we have an unempty subset of natural number, and then it must have a least element. All right, by the will ordering principle, S has a least element. Because we don't know the fundamental theorem of arithmetic applied here. We actually want to use this one to prove that. So we know that that's a prime factor, but we don't have that yet. All right? All right. So by the will ordering principle, this implies S has a least element. Let's say P and S is going to be in S, the least element in S. I claim that P is a prime. P is a prime. And of course, once we prove this one, now P and S, we are done basically. Implies that P is a divisor of n, all right? And which means that n has p as a factor. So this thing in itself, this is statement 5. D is a positive prime divisor or prime factor, where we take the word factor, prime factor of n. So all what we have, we need is to prove this equation. All right? And to do this, first we know that P in S implies P is bigger than 1, and P divides N. All right? Now, let's assume if possible, all right? If possible, that a Q, all right, does not equal to P, or Q does not equal to 1, and Q divides N. Basically what I'm saying here, let's assume that actually divides P, I'm sorry. In other words, let's assume this P is not a prime, basically. And I'm saying that if possible, okay, you can imagine that they're going to say, well, this is going to lead to basically to a contradiction. All right? So let's assume that there exists another divisor that is neither P or 1, okay, and that it divides. Then we have Q divides P and P divides N, okay, from here, because P is in S. Then by the transitive property for divisibility, this implies the Q divides N. All right? And now this means, what does this mean? This means that the Q is actually in S. All right? Because the Q is not equal to 1, actually it is bigger than 1, and the Q divides N, so it must be in S. Well, let's see here. But since we are assuming that the Q divides, this implies that actually the Q is smaller than or equal to P, but it's not equal. So it means it's strictly less than P. This is a contradiction. It cannot happen because P is the smallest. Okay, so this is not possible. This means there is no Q. Okay, so you could say it either by contradiction or say this means this implies P has no non-trivial factors. Non-trivial factors. By a trivial factor means because if we are given any integer, all right, or positive integer or natural number, all right, that's not equal to 1, then always 1 and the number itself are divisors, and we call these are the trivial divisors. So hence, yes, it does imply that P is a problem. All right? So we have that taken care of. All right, after all of this, we are ready to state or put the exact statement of the fundamental theorem of arithmetic. All right? This is theorem 3.2. Okay? This is fundamental theorem of arithmetic. From here on, we're going to denote this is by FTA. And it states that every positive, every natural number n is either that does not equal to 1 is either a prime or a product of a finite number of primes. And this prime need not be distinct. Okay? So it could be the same, or it could be distinct. All right? Moreover, the representation, of n as a product of primes is unique apart from the order of the primes in, or the order in which the prime factors, prime factors occur in the problem. This is what is called the fundamental theorem of arithmetic. Something we have used many times, probably without knowing the name of it. Okay? All right. The proof of this is actually we're going to be using one of the results that we already proved. All right. So let's just start with the proof. We know that since n is a natural number not equal to 1, means it belongs to either the prime classification or the composite classification, either in this type or this type. Then either in is a prime or n is composite. Now remember, n is given, so it cannot be both of these. So it must be either this or this. Now, if it happens this given n is a prime, then we are done. For this particular n, but this statement is true for every natural number, then we need to look at the other possible. Again, on the other hand, if n is composite, then by the previous theorem, n has a prime factor let's say P1, that this is going to be bigger than 1, all right? And n is going to be this prime factor times n2, where for some integer n2, or some n2 natural number, that is actually smaller than n, but it's going to be also bigger than 1. Because if it is equal to 1, then n is equal to prime. That's not 1. Okay? And it can, in 2, it cannot be also n because P1 is bigger than 1. All right. Now, again, if n2 is itself a prime, we're stopped and we are done. All right? Put this one in here. And as you see, we're going to repeat actually this argument. Or we could use actually mathematical induction. And actually we did use mathematical induction to prove the first part of the fundamental theorem, which talk about the existence of the prime factorization. The only thing we do not do is the uniqueness, and that's what we're going to do next, of course. All right, now, in here, if n2 is a prime, then we are done. If n is equal to p1 n2, where p1 and n1 are prime, or n2, sorry. Did I say n? Let me call this is n1. I don't know why. I don't know how to put it n2. n1, okay, for some n1. We will get to n2, but so here. So this is n1. So then we have this one. This n is equal 1, where p1 and n1 are primes. And we are done, okay? And we are done. If not, if n1 is composite, means it's not a prime, again by the theorem, what's the previous theorem? There exists a prime factor, prime, such that n1 is going to be equal p2 times n2. All right? And with this implies n is going to be p1 D2, N2. Now we're going to continue where this N2 is going to be less than N1, and this is going to be bigger than 1, all right? This is a prime, there is just a prime, so it's bigger than 1, all right? And this one itself is less than, of course, the original number, N, all right? Now, we continue this, and then we're going to produce a descending chain of integers. Okay, so we continue this process. This process, and have a descending is decreasing, okay, chain of positive integers, positive, yeah, I will say integers of this form. 1 less than, we actually write it backward, okay? Make it easier to see. So this one n bigger than, n1 bigger than, n2, and so on, up to n sub k. All right, I claim that this chain must terminate, and this chain must terminate with nk is a prime. Let's say right, because it's decreasing, okay? So, and it is, we know that this is positive integer, so we cannot go for, for it. And the net result, therefore, we're going to see that n is going to be d1, d2, and so on up to dk. And this proves that where all these di's are. Okay, so this proves actually the existence, all right, of prime factorization. The next thing we want to do is prove the uniqueness. Okay. Next, we prove the all right. To do this, what does this mean? What does it mean to prove actually the uniqueness? So is that because the uniqueness of maybe of the prime factorization? Okay, that is that here. So let's assume that n is a product of these two primes, d1, d2, up to d sub r, and n has some other primes that give n and there might be a different number. So we have to assume this, where Pi, U, J are primes for all I between 1 and R, and J between 1 and S. And of course, R and S bigger than or equal to 1, these being integers, all right, positive integers or natural numbers. All right, now since both of these expressions is equal to n, then what we have P1, P2 up to P is equal to Q1, Q2 up to Qs. Okay, and both of these are equal to n. Now, we're going to consider one other thing. I want to actually also have these ordered, okay, without loss of generality. We take this one statement out. Okay. We also assume without loss of generality that the P's are ordered according to their magnitude, starting with P1 less than or equal to P2, and so on, PR, and the Q's are ordered in a similar way. Q. All right, we're going to start actually doing the uniqueness by induction on n. Okay, so we proceed by induction, actually strong induction, on n. The first value of n is 2, okay, for n equal to 2. The statement is true. Statement holds since n is equal to 2, and this is the only way you could express 2, right? In terms of a prime. Itself is a prime. All right? So now we're going to assume that this statement holds for 2, 3, 4, and so on. Okay? So let's assume that the statement holds. Means if we have a natural number that we know it can be written as a product of two of primes, then the representation is unique. So we're going to go with this. So we're going to consider n. Okay. And we know that if n is a prime, then the statement we have this is actually let's suppose that the statement is true rather. Okay, we say suppose that the statement concerning uniqueness. So we know the existence of the prime factorization. Then uniqueness holds for 2, 3, 4, and so on up to n minus. Now, consider a natural number. Well, so if n is a prime, then there is nothing we have done again. If n is a prime, then we are done. But again, remember this is true. We want to show this is for every. So one of the possibility is this number that we're working with to start with is actually itself is a prime. And suppose it's not. Assume that n is composite. And by the third part, I know that, all right, then n, you can assume it has this one, B1, B2, up to BR, and n is equal. Actually, this is where I want to start my argument, QS. Okay, where we have, and we are arranging these, and B1 is less than or equal to B2, and the Q1s are this. But this time we have the R and the S are going to be bigger than one, all right? So we're not assuming that these are primes. So there must be at least two, all right, in each side, more. But we will show that they must be the same number. All right, now let's look at applying actually corollary 2. Okay, so we're going to apply corollary 2. So let's write this down. So we have P1, P2 of PR is equal to Q1, Q2, Q2S. All right, we're going to apply corollary 2. Remember what corollary 2 says, that if you have a prime that divides a product of other primes, then that prime must equal one of them. So in here, we can say that P1 divides Q1, Q2 up to Qs. Because this Q's is a multiple of P1 with other P's. Okay? Now by this corollary 2, this implies that P1 must equal Q sub j for some j between 1 and s. Similarly, we can apply corollary 2 in the other way. We also have Q1 divides B1, B2 up to BR. And this implies that Q1 is going to equal B sub I for some I between 1 and R. Okay, well, let's put these together. So we have P1, all right, is actually the smallest. So this is less than or equal B sub I. The I in here, this one right there. And I know this is equal to Q1. And I know this one is smaller than or equal every Q Q sub j, and this is equal to P1. All right, well, let's look at that, this sequence of inequalities. So this means that we are squeezing in the Q1 between P1 and P1, which means they must equal to each other. So this implies P1 is equal to Q1. Now, with this, then I can cancel out the P1 and the Q1, and then we have this left to apply the induction hypothesis to. Okay? So now we consider the number n over P1. All right? I know that this is less than n since P is bigger than 1. Then by the induction hypothesis, all right? So by the induction hypothesis, since, let me actually, before I do this one. All right? So this case we have n over p1 is going to equal to p2, p3, and so on to pr. And also this is the same as the q's without the q1. So q2, q3, up to qs. Now, we are by the induction hypothesis, since this one is less than n, all right, and this is two representation of a number that is less than the induction hypothesis says that these s and the p's and the q's must equal to each other, all right? By the induction hypothesis, because we assume that this is true for any up to n minus 1. And when we have this one, it's going to be one of those integers from 2 to p minus 1. Okay? By the induction hypothesis, we have the E pi is equal to, first of all, R is equal to S, and DI is equal to QI for every I between 2 and I. And since we also assume prove that the P1 and the Q1 are equal, then we are done. So by that induction, this takes care of the whole thing. All right, a few other things left. And so we know that every natural number can be written, it's either itself as a prime or can be written as a product of a prime. We have a special way to express this n as a product of primes, and we're going to put this in a corollary. And it says that any natural number n bigger than 1 or does not equal to 1 can be written uniquely in a canonical, it's called here, or standard form. And this is the way it is written as D1, alpha 1, D2, alpha 2, up to B sub K, alpha K, where the PIs are primes with are distinct primes actually. These are distinct. Prime. And the exponent and alpha I is bigger than or equal to 1 for every I between 1 and 2. And in general, also, we usually take the p's to be listed in a increasing order. So start the P1 being the smallest up to Pk. No equality between these. So we call writing n in this form as standard, okay, factorization or standard form of expressing n as a product of primes or a canonical form. Of course, this is nothing to prove in here because all what we are doing is we are collecting the different primes in a prime factorization of n, and since the multiplication of natural number is commutative, so and associative, all kinds of stuff is going on there, then just the way we express this, all right? Now, in some cases, sometimes when we want to write a canonical or standard representation of a natural number, we might allow some of the alphas to equal 0 in cases where it's not going to affect anything, okay? So that we have the same primes appear in two numbers, okay? For example, if I take the number 12, okay, and the prime factorization of this is 2 squared times 3, all right? And let's say we take another number in here, for example, 36, all right? And, or actually we took 20 or 50. Yeah, this one is not going to help. Here is 15, which is 3 times 5, and all these to the power 1. Sometimes for convenience, we could actually express this by putting 5 to the 0, because the 5 appears on the other number, it's not in the fifth. And this one, we could write this one as 2 to the 0 times 3 times 1. Okay? So the prime in both numbers appear without affecting their actually numerical value or their magnitude. All right? Now, next we're going to look at this property of uniqueness, all right, of factorization. Turns out, it is a very important property, and it's not always guaranteed or satisfied by other, mathematical systems or number systems. And I want to give a couple of examples of those where it doesn't hold. Let's consider an example. And in this example, the unique factorization equation does not, let me put the property, does not hold. Does not hold. All right, so let's consider the set of even natural numbers. So E stands for 2, 4, 6, 8, and so on. All right? Where K goes from 1 to 10. Okay? And I think this is as a set. Okay? Now, we need to define the concept of a prime. What do we mean by a prime? So we define the prime, or what we call E prime. It's some sort of a different E prime to be an element in E that is not a product of two elements in A. And really, this is kind of what it is for, primes for natural numbers, all right? For example, the E prime, some of the E primes in here is 2, 6. Other ones we put in the list in here, 10, 14, and so on. Right? None of these can be written as a product of two elements from here. 2 itself, right? This one is 2 times the 3, it's the only way, but the 3 is not in E. So this is a prime as far as this system is concerned. Non-primes, E primes, means composite basically. And here the 8, 12, 16, and so on. All right? Now, it is not hard to show that this set E, it's closed under addition. Means if you take any two of its elements, you add two even numbers, you come up with an even number. Okay? And if you take any two elements from here and you multiply them, you come up with an element from here. So we express this by saying that E is closed under addition, multiplication, all right? And these operations are commutative, associative, distributive, and so on. So this mathematical system, actually, that satisfies all these nice properties, like the the natural numbers, all right? Except it lacks one, which is inverses, the additive inverse. Yeah, it's almost like actually it is a ring. Actually, if we take the positive and the negative of these, positive, negatives, maybe I could make an amendment to myself. So this one with this, E is a ring. It's a mathematical structure that is very important. So it's very much similar to this. This is similar to that ring of integers, all integers, all right? Now in here we can see that the unique factorization does not hold. For example, you can take 60, and this is 2 times 30, and both of these are E primes. Okay? And so this is one way to write this, and you could write this one as also 6 times 10. And again, these are E primes. So we have 60, and we are able to express it as a product of all primes in this system, and so we don't have uniqueness. So the prime factorization here, if E is not unique. Another little more sophisticated example, I just want to write it down here for you to think about. It's something that we're going to be using very often, but for the sake of illustrating the significance of the fundamental theorem, because it makes life easier when you have that unique factorization, by the way. It's this. Here's another example. If you take, this is called the Gaussian integers, okay? The Gaussian integers is you take the square root, let's say, of 6i. This consists of all numbers of this form, a plus b square root of 6i, where a and b are integers. Again, it is not very hard to show that this set, this one is enclosed under addition and multiplication. What does this mean? When you take 2 elements from here, you add them, you're going to come up with an element of the same form. When you multiply these as elements, as complex numbers, okay, you're going to come up with an element in this form as well. Because A and B are integers, all right? Now, this also happens to be actually a ring, all right? And then you need to know how to define probably what do we mean by primes? When we define it in the same way. And if you take 10, then you know that you could write these times 5, and 2 and 5 can be written in this form, because this one is equal to 2 plus 0 square root of 6i. Okay, and the same thing with this. In other words, that in C, all the integers are contained in here. All right, where you take the B part is all equal 0 is here, and then that's you can write every integer in this form. On the other hand, you see this one also can be written, which you can actually multiply out and check if this is true. This gives you 10, because these are actually conjugates to each other, and when you multiply them to the I, it's going to cancel out, and you end up with this is 4 plus actually 6, give you 10. So again, unique factorization is not satisfied in this system. All right? The last thing I want to actually do in here is look at some applications of the fundamental theorem of algebra, of arithmetic. One, we want to look at how we can translate the divisibility of 2 integers using the prime factorization.
And then we're going to look at how we find actually greatest common divisor and least common multiple using the prime factorization. So here's some applications. Let's just start with this here. Then let A. And by the way we could write the prime factorization, we could use this multiplicative notation, like the summation notation. And in here we want to put I equal 1 and R B sub I alpha sub I. Okay? Where this one be the standard representation of A. Now remember in here that means the alpha i's are positive, the i's these are prime. Okay, so whenever you use this standard representation, that's exactly what this means. All right. And then I let E be a positive integer. Okay, so this is in N. Then what does it mean that actually A divides B? Okay, then B divides A. Then B divides A if and only if B is written like this. Actually, I equal 1 to R BI beta I, with the betas, some of them could be 0, and they must be less than or equal the alpha i's, and for each I between 1 and R. So this is an if and only if state. Okay? So if we have B is divisible by, or B divides A, then this condition is satisfied and the converse of this. But this is very, very easy question. So let's just start by assuming B is equal to this. Okay, so here it is. Assume that B is this part. Equal 1 to R, BI beta R. All right? Need to show where these satisfy this. It's very important. The beta I less than alpha. Okay? For every I. Need to show B divides B. All right. Let me do a little trick on the exponent and the product. Now B, I know this is equal to this. And I can write this one by E beta I minus alpha I plus alpha I. So I'm adding and subtracting, these values. Actually, let me actually start with A. I'm sorry. I want to do the A. So I want to write A as a product, okay, to show it is there. Okay, so this is equivalent to showing that A is equal to B, C for some C a natural number. So I take everything natural numbers if you don't want to go with anything. Well, those statements are true, right? So let me start with A. So this is equal BI alpha I. Now this is the one I want to add and subtract BI. So this is alpha I minus beta I plus beta I. And then I'm going to separate this into two products, okay? First of all, I start with this. The exponent, I can put alpha I minus beta I multiplied by beta I. Now remember what this product means. This means that when we take I equal 1, we plug it inside the the product, and then we take 2 and we multiply everything. So we can still write this one as using two product notations. The BI, alpha I minus beta I. Then we have the B beta I equal 1 plus. The second product in here, this is equal B. And this one, we're going to see if it makes sense. Meaning we're not going to get any negative exponents in here. All right? Now, it's not very hard to see, okay, that this exponent is actually bigger than or equal to 0. Okay? To see that, let's look at the condition on the beta i's. Since 0 is less than or equal beta I is less than or equal alpha I, this implies that if you subtract the beta I from here, I don't care about this side, then we get 0 less than or equal alpha I minus beta I. And this is true for everything. So this means that the exponents on here are all non-negative, either 0 or positive, and I'm going to call this number C. And now we do have A is equal BC. So it actually does divide. The converse of this statement, okay, so let's assume that B divides A, and I want to show that B has this particular form. All right. Going this way as opposed to the proof. So let's assume that B divides A. You need to show B is written the way it is written. I equal 1 or I beta I, and these ones are the beta for every I. Alright, let's go ahead and see what does it mean B divides A. This implies that A is equal to BC for some C. And let's assume that that C is equal. I'm going to use the same primes, all right, as in for. Because from here you can see that the prime factors of C, okay, the prime factorization must be the same as in A. Maybe some of them are missing if they don't appear. Okay, let me actually write this down. Since by the fundamental theorem of arithmetic, the prime factors of A and C, as well as B, of course, as well as B, are NBR. How am I going to say this one? I don't want to say the same saying, but I'm trying to find a nice way of expressing this. Let me see if I have this one. Yeah, okay, so the prime factors on the two, let me say the two sides of this, which is A and C, are, there is no prime factor. There is no prime factor of A. They're going to be different. Let me see. By the fundamental prime factors, A and C cannot be different. So I cannot have an A has a prime and the C does not have that one. Okay, but they might, some of them, as I said, missing. All right. So we're gonna take the notation and express C using all the primes in A, but some of them could be equal to 0, their exponent. So let me put that, where the gamma I is bigger than or equal to 0, and this is actually less than or equal also to actually, this is it. I don't want to say even any restriction on this. That's all what I'm saying. So these are going to be bigger than or equal to 0. Some of them is actually is equal to 0. All right. Now let's look at when we have A, which is this implies A equal BC implies that the I equal 1 to R of BI alpha I is equal B, all right, and multiplied by I equal 1 to R B I gamma I, all right. Again, let me write actually see what's the only thing I need to show is that the exponents for the B, they satisfy this, okay? So let me actually also write a okay, so let's again say this one is I equal 1 to R B I alpha I is equal, I want to write the prime factorization of B. I equal 1 up to R B I beta I, and this is multiplied by, and then we're going to get the exponent to be the correct exponent. And this is the product of BI gamma. Again, we're going to combine these into one, okay, product. And then again, we're going to be using the prime factorization, the uniqueness. So this is I equal 1 up to R, the I beta I plus. I want to put them into one and then combine the exponent. Now, by that unique factorization, or by the uniqueness of the primes, because these two numbers are equal, we must have the exponent must be all the same. It implies that the alpha I is equal beta I minus plus gamma I. And now solving for beta I from here, we obtain that this is equal alpha I minus gamma I. Now let's see if this would satisfy this condition. Okay, let's see this one. So we have the beta I know it is bigger than or equal to 0 because the prime that appears on the two sides of that A equal BC must be the same. Some of them could be missing. And now, with this equal to alpha I minus gamma I, and this is less than or equal alpha I, because those gammas are bigger than or equal to 0. So you subtract each one of, each one of these from alpha I, the alpha I is going to be big. So it does satisfy this condition. All right. Let me see how much is left. I hope not very much. Yeah, I want to just give a theorem that gives us the greatest common divisor and least common multiple, all right, of two integers. And that's it. I'm just going to end this last theorem. So let's give us another way to calculate greatest common divisor and least common multiple. Unfortunately, it is not efficient. When the numbers are very big, this becomes very, very hard because it requires us to know the prime factorization, which is in itself is not easy. It's a harder problem. All right, so here's the theorem, last theorem. Let A equal I equal 1 to R, Bi alpha I, and B equal this. And this time I'm going to be using the same prime. So I'm going to allow some exponent to equal 0. Okay? I equal 1 to R, Bi, beta I, where the alpha I and the beta I's are bigger than or equal to 0. Okay, for every R. So these are the prime factorization. The modified, if you like to say, modified standard representation of A and B. The modified means I allow exponent to be 0, okay, of A and B. Then, the greatest common divisor is going to be equal to I equal 1 to R, Bi, and in here we take the, actually the minimum of alpha I, beta I. Okay? Now remember the minimum of two integers in here or two natural numbers, it's going to be either one of these, but it's going to vary from one prime to the other. And the greatest common, the least common multiple is we take the maximum. Okay, Bi, we take the maximum. Alpha I. All what we have to do is really prove one, and then the other will follow from the relationship between them. Okay? Well, let me proceed to the proof. So I'm going to call this. And here I'm going to denote this is by D. Okay? So this equation claims that the greatest common divisor is expressed this way. So what I'm going to do, I'm going to name this is D and show that actually D is a common divisor, all right, of A and B. And if there is another common divisor, all right, then it would actually de-divide that, all right? So let's, for that divisor to divide D, all right? So let me do this. We're going to let D equal I equal 1 to R, Di the minimum of alpha I beta I. All right, now let's see why this one, and also we're going to let Mi equal the minimum of alpha I beta I. So with this notation, then D becomes equal Bi Mi. All right. Now let's see why actually D is a common divisor. So we have D divides A and D divides B. Why is that? Since this Mi, all right, is bigger than or equal to 0 and less than or equal actually both alpha I and beta I. So by the previous, from a previous theorem, actually from previous theorem. Remember that A divides B if the exponents, all right, of this divisor, the number that divides, is actually less, and it does satisfy. Now, let's assume that we have C divides A and B. All right, so let's go with that. Assume that C divides A and C divides B. Simply we are assuming that C is a common divisor. All right? And let's assume that, again, remember this means that both A and C, all right, you put K in here, and B equals CK prime. So again, the primes in the two sides of this equation in here, all right, they're going to be the same. So we can use, again, the modified representation of C like this. Okay, C is going to equal I equal 1 to R, Bi some other exponent, where these gamma i's are bigger than or equal to 0. All right. Moreover, we have also that the gamma i's is going to be less than or equal alpha i's, and gamma i's is going to be less than or equal beta i's. All right, because it divides, means that this side it might have a bigger, okay, actually exponents. All right, but we have in here, since this minimum, mi, is less than or equal to both alpha I and beta I for every I. All right, between 1 and r, and everything is true for every score. Then we have let me see in which direction we can say this one. Yeah, this means that then actually C is going to divide D. All right, because the exponent of it, all right, is going to be less than, since, let me see how we're going to actually see this. All right. So we have the mi and these are the exponents of the d, okay? And since they are smaller than, yeah, this is 5 for the theorem. Yeah, we are done. So which means that actually d is the greatest common divisor. The final result is for greatest common multiple, which follows immediately from this formula. Okay, we have AB. Remember, we proved this one is equal to AB. Everything is positive divided by AB. All right. So this is equal to, when I multiply these together and think of using the modified alpha I times another one, I equal 1 to R I beta I. Now we're going to divide this by the greatest common divisor, which is now we know it is for 1 R the I, and this is the minimum. Alright, so we can combine these into one. That's in the numerator one product. The I plus beta I. And this is the minimum. Okay, so it's just even like this. I equal 1 R di minimum alpha I b. And again, we could use the dose of exponent, and still we can bring this up, and this becomes I equal 1 to R b sub I alpha I plus beta I minus the minimum of alpha I beta I. I claim that this is equal actually the maximum. So the last thing is a claim is alpha I plus beta I minus the minimum this is equal to the maximum of alpha I beta. To prove this, actually we can drop these I. We just can do it for any two numbers. And this is true for real numbers as well. It's not just the natural numbers. Yeah, remember this is by cases if you wish. So here, so this is what I need to show, that the maximum of two numbers is equal the sum of these two numbers minus the minimum. Maybe. Let's take A equal B. This is case 1. Then the left side is equal A, and the right side is going to be twice A minus the minimum is going to be A, and this is equal A. Let's look at the case where A is less than B. And our symmetry in the other case will follow. So the left side is going to be the maximum, and that's going to be B. The right side is going to be the sum of these. That's going to be A plus B. And then you're going to subtract the minimum, which is going to be A. And this is equal to B. All right? So this is it. So let's take care of this. And we're going to stop right here first. Actually, before we do this one, there's one last term in here. Let me just point out to it. And yes, we did prove this earlier using the will ordering principle. But here is another way. It's theorem that is credited to Pythagoras. Theorem 3.2. Okay, it says that square root of 2 is irrational. All right. The proof given in here is using again the fundamental theorem of arithmetic, and it's the standard proof more or less that you would see. I'm not going to go through the proof. It's by contradiction. I just point out to what it is. So you assume that square root of 2 is a rational number where the greatest common divisor AB equal 1. And remember that A and B are natural numbers. Then you square both sides. All right? And you multiply out this. And then you compare the primes in the two sides of this, and then you're going to argue that the greatest common divisor is not going to equal 1. Okay? So I can leave the details for you. Okay? And remember, we did actually prove this using the will ordering principle. All right? It doesn't use, in other words, very sophisticated, or the sophisticated, if you wish, fundamental theorem of arithmetic. All right.